alone in this universe. So it is going to be an exciting session from our point of view, and from the responses that we receive from the queries, participants, and our audience, that they are really interested to take part in this program. So those who could not attend today's event, so we will put this video on YouTube as well and our Facebook page, so they can have a look at it once the program is over. So welcome again to today's session of Yuri's Night 2018 celebration. Let's welcome Sutam Satyal to today's program.
Thank you. So you guys can all hear me, right? And the audience. Okay. So here's my slide. Can you guys see my slide? So my slide.
Just write down.
So I'm gonna start it. So if they have any questions, so is there a way they can ask, or how does it work?
There's a way they can ask. They can write and give it to me, and I can ask you. I think that will be an easy way to interact. Or they will come here and ask, because we can on this video from both sides, so we can record the interaction as well.
Oh, okay. No, I just wanted to make sure. So there's only one mic at the front. Okay. So can you guys see this?
Slides, we are getting blank.
So, did I share the screen? Maybe not. Hold on. That's right.
Okay, yeah. Yeah, we can see your slides now.
Okay, great. Yeah, that's it. Projection. Let me this thing.
Now you can uncover your video as well.
Okay.
Okay.
I was just everything. Hey guys, my name is Sutam Satyal. I work here at the University of Texas at Arlington. I do a lot of things here. Research is my primary thing. I do research on exoplanetary science. I'm also a lecturer. I teach electricity magnetism, at least this semester, to undergraduate students. I'm also the undergraduate lab supervisor here. So today I'm going to talk about a new era of exoplanetary science. Is there an Earth 2.0? I mean, is there any other planets, similar to Earth or Earth-like, or, something that has life, life similar to Earth? This is an interesting image that I found yesterday. It's a Kepler array, meaning each of these are the stellar systems, similar to our solar system. Solar system, you'd see 8 planets around its orbit. So these are Kepler systems, meaning the star systems that were discovered by Kepler Space Telescope. You see some of the planets that are very close to the star are very fast. They're orbiting very fast. I think there are about should be about 33,000 of these planets here. I'll get to the numbers in a minute. So let's just start the talk. Quick, I always like to thank my collaborators, the people who I work with. The top ones, and these are the one here at UT Arlington, I collaborate with PhD students here. My collaborator and my colleague, uh, Billy Quarles, is at Oklahoma University. Others are from various states. Nader is from Hawaii. Tobias is German. Right now, he's working in Kasi, South Korea. Uh, and I'm also working on a project with Jerry in San Diego State. I also help undergraduates, to do research. The current one being John Griffith. You guys may know I also work with Suresh. I've been working with him in two projects at NASO. So I will talk about exoplanets, habitability of exoplanets. One case study uh, of GJ32 system, that paper I recently wrote um, and published, and conclusion of today's talk. So the universe by numbers. Are you all with me so far? I guess Suresh muted the mic, so that's okay. So this slide is to give you a perspective of what we know in the universe. These are rough estimates. There are about 200 billion galaxies in the universe. If you do some hard Google search, you'll find this number may vary. There are some reports up to 400 billion galaxies. And each galaxy have stars, like our Milky Way galaxy down here. You can see bottom the animation, or to the right. Milky Way galaxy is one of such 200 billion galaxies in the universe. The universe is something that has everything, all the matter, all the energy that we know. Um, and also the energy that we don't know, like dark energy and dark matter. So of these 200 billion galaxies, Milky Way is one of them. And each one of these galaxies have other somewhere from 200 to 400 billion stars in it, right? So now you can imagine how many planets can be there in one galaxy alone. Okay? So rough estimate here is somewhere from 200 billion to 2 trillion planets in our galaxy alone. And given that, let's say one star has, anywhere from 1 to 10 planets. Like our star, our sun, has 8 planets around it, or 9 if you still consider Pluto a planet. And I know some people still do that. That's okay. So all these planets that are outside our solar system, we call these extrasolar planets, or in short, exoplanets. Right? The farthest planet that we know is about 28,000 light years. That's a lot. That's quite a lot, a long distance. The nearest one is around Proxima Centauri, Alpha Centauri star system. That's about 4.2 light years from the sun. If you see at the bottom image here, this is our Milky Way galaxy. Our solar system is somewhere at this point here. All these dots, white dots you see, are mostly the stars, among these 200 billion stars. This distance from our Earth to center of the galaxy is about 26,000 light years. So the farthest planet is even on the other side, the center of the galaxy. And when I say these nearest planet, farthest planet, that's something we have observationally detected or observationally verified, right? When I say 2 trillion planets, these are possible planets that we can have, right? These are based on simple probability calculations. um, we'll get to the numbers that we have calculated so far in a minute. So exoplanet observation, how do we observe, uh, you know, these planets? There are two main methods, the ground-based, using the ground-based telescope or the space-based telescope. Um, Both of these telescopes, they use either the transit method or the radial velocity method. I'll discuss those methods in a minute. These are just simple pictures here. This is a Kepler Space Telescope, the telescope that's been running since 2009, and it has found hundreds, thousands of exoplanets, and there are a few thousand other planetary candidates that are yet to be confirmed. This is the land-based, telescope here in Texas, West Texas, called McDonnell Observatory. This TMT, the 30-meter telescope, is not yet built. This will be the largest telescope when it's built. The problem is they don't know where they're going to uh, put this telescope. Initially it was planned uh, to build on the Mauna Kea mountain in Hawaii, but that's all been uh, canceled. So they are looking for a good spot. That's why I've been telling Suresh and other people in Nepal that we need to make such telescope somewhere in the dry region of Nepal, and that we need to start lobbying for this. First, write a paper, find a suitable ground, suitable region based on the climate and what part of the sky can we survey using these telescopes, and we can send requests uh, to these people who are making this telescope. If they want to make such telescope in Nepal, that would be quite an achievement, and a great facility for all the new students who wants to work in astronomy and astrophysics in the future. This James Webb Space Telescope is, it was supposed to be launched next year. This was supposed to replace Hubble, but it's canceled for next year, and that they'll try again in 2020 or 2021. This transiting exoplanet survey satellite, it's called TESS. TESS satellite will look specifically for extrasolar planets in our stellar neighborhood. And this TESS will, eventually replace this Kepler Space Telescope, which is almost retired, or actually it is running out of fuel and it might die any day. So this new space telescope called TESS is going to replace the Kepler, and this TESS telescope, will give up, uh, will collect lots and lots of data, and by analyzing those data, we can find other exoplanets, uh, mostly Earth-sized planets in our stellar neighborhood. These are some of the detection technique that I mentioned before. This is called radial velocity method, or RV in short. Um, this is an indirect way to find any planet. Like for example, when a planet like this one here, when a planet orbits a star like this, uh, it wobbles the movement of this star. There's a gravitational pull due to this bigger planet outside, and the center of gravity is slightly outside of the star, or we can say both of these bodies, go around a very center. So that means as this star, moves in a circle, or it oscillates, um, like in this figure here, when the star is moving away from the observer, let's say we're here at Earth, observing the stars using a telescope, then as you can see here, when the star moves towards us in this orbit, its light is blue shifted. It's called the Doppler shift method. Um, or the Doppler velocity. And when the star moves away from the observer, the light coming is red shifted, and measuring this shift in the light, you can tell, you know, um, or you can first get these radial velocity curve like this, and from this curve, what they tell is uh, or what we can find from this curve, the phase versus RV. RV here is in meters per second. We can calculate the period of the planet, like how much this star oscillates, depends on the size of the planet that goes around it. And of course, the distance from the star, how far it is from the star, and simply extracting information from these RV curves, we can find the planet's period, like how long does it take for the planet to go around. um, if we know the inclination of their orbital plane, we can also calculate the mass of the planet, uh, and we can also uh, calculate the a stellar velocity, how far the star is going from these type of curves. If you have done Kepler's laws, or you might do sometime in the future. If you already know these things, I do have a homework for you guys to find the planet mass. Use the Kepler's third law and use conservation of linear momentum, and you can get how big a planet is, like just for this curve here. This has amplitude, it has a period of about 4.2 days and amplitude of about 50 meters per second. And as a matter of fact, this curve you see here, this is the first data collected for the first ever exoplanet that was found by Swiss astronomers uh, Mayo and Quilo, and the planet was called 51 Pegasi b. We'll talk about that planet in a minute. And the other one is the detection, the transit technique, and the other detection technique. This one is again a very simple and elegant method that uses the eclipsing of a planet around a star, of course. So whenever a planet like this one, this blue dot here, pass around the star, its brightness decreases. That happens here in our solar system during Mercury transit and Venus transit. First we collect the data as we receive from the sun, right? Call that one. But whenever any object, like this planet here, pass through the star, that light, the flux, the luminosity decrease, and based on how much this flux is reduced, its depth can give us the parameters such as the radius of the planet, the inclination of the planet, and some other information like distance, the semi-major axis, how far the planet is from the star, and such orbital parameters. I'd like to remind you that these are not direct detection. We don't use optical telescope to actually take a picture and find these planets. So far, these two techniques are very popular and have found hundreds, thousands of planets. Though indirect, it's an indirect method, but these are being very effective. Uh, this one, I'm sure you all know Manisa. She works at NASA. She took this picture of Mercury transit, as you can see. Maybe you cannot, but if you get closer, there's a small black dot here. It's very hard to see. That when the Mercury was transiting our sun, so that means if we are recording the flux of our sun, we would see this straight line, and whenever the Mercury would transit the star, our sun, we would see this kind of uh, depth in the brightness, and from this depth, we can fit these curves and get the orbital parameters of the uh, planet and the star. So, uh, so this discovery read some, history of the exoplanets, the Gamma Cephei AB. This was the first exoplanet, but it was not confirmed. And this Gamma Cephei is a binary star system, meaning there are two stars that go around each other, around their very center. And one of these stars had a planet, and we call that Gamma Cephei b. It was unconfirmed in 1989, finally confirmed in a confirmed exoplanet, the RV curve that I showed in the previous slide, called 51 Pegasi b, was found in 1995, not long ago. It's about 20 years ago. We had the first exoplanet, confirmed exoplanet, and in the past 20 years, that number has increased to 3,510 confirmed, and there are more than 4,000 candidates. So you see, from not knowing that there are planets outside our solar system 20 years ago to now, we have confirmed these many, and there are still thousands of candidates, and there are more telescopes like TESS I mentioned earlier is being launched to detect more planets. So these statistics is what gives us hope that there has to be Earth-like planets out there in our galaxy, if not outside our galaxy, in other galaxies. Of these confirmed planets, 584 multiplanetary systems, meaning they have more than they have more than two planets. Solar system is the largest one so far. We have 8 planets, and there is this planetary system called HD 10180 that has 7 confirmed planets, and 2 are yet to be confirmed. So if these are confirmed planets, then this system will be the largest stellar system. 14 exoplanets are in habitable zone. Of these planets that we know, 14 of them, are in the stellar habitable zone. What is a habitable zone? Habitable zone is a region around a star where liquid water can exist. That's a short definition. Of course, there is a lot to that, but if that zone, also called the Goldilocks zone, receives the right amount of radiation from the star, not too close to the star, then all the water would evaporate away. Not too far from the star, so that not all the water gets in the frozen state. So the right distance, similar to Earth, we get the right radiation from the star, and this region is called the habitable zone. And there are about 14 exoplanets that are within this habitable zone. Some examples like Kepler 186f, TRAPPIST-1G, Exoplanetary Archive, Caltech. If you go to this site here mentioned, you can confirm all these information that I just wrote. I'm just citing where I get all this information from. And these Kepler confirmed planets, you see most of these planets that we have found. This is just a simple data showing that the majority of the planets that we have discovered so far are less than 100 days periods. So they are closer to the Earth, closer than Earth. If we compare the Sun-Earth system, they are very short period planets, meaning their 1 year, is less than 100 days. Most of them being around, 10, about 10 days, maximum population lies year in 10 days, meaning you know, these planets have very short year, or the orbital period is very short, about 10 days. This bottom one you see here, number of detection discovery year. You see in 1995 here around, this is when the first exoplanet was found, and now as you see 29, that's when the Kepler was launched, and 10, 11, 12. All these green are transits mostly from the Kepler Space Telescope. In 2014, that rate went up to 1,000. 15 was a slower year. 2016, more than 1,500 planets. 2017, we're counting more to come with newer space telescope that are being launched. So uh, I didn't need that. So these are some of the potentially habitable exoplanets that are known, like Proxima Centauri b, TRAPPIST-1, Gliese, Kepler, Gliese CF. Here you'll understand this diagram more if you look at the index. So this is called the Rank by Earth Similarity Index, ESI. So Earth is 1.0, right? So that means Earth is habitable. It is at the habitable zone. It is a rocky planet. It has to be rocky planet for to be habitable. At least if we take Earth as an example, like the other two planets, Neptune and Jupiter, shown here, have this index much less than 1. So if this number is close to 1, then we can say the planet is habitable. But in this case, it's much less than 1, like Neptune and Jupiter. We don't expect it to be habitable. It is not a rocky planet, first of all. It is all gas. So it's all, it's enveloped by hydrogen and helium gases around it. And plus, this is not in the habitable zone. This is much farther out from the habitable zone. So that's why this is less habitable, much less habitable compared to Earth, which has ESI 1.0. If you look into these planets, you'll see that Proxima Centauri b is 0.85, and TRAPPIST is also 0.85. So these two are the closest one to the Earth. But the problem is it's not 1, remember. So that means they still, first of all, we still don't know much about their atmosphere. Their sizes, they may vary a little bit. So if size varies, and their atmosphere will vary, because if a rocky planet has a smaller size, it has less gravity and it cannot hold the atmosphere, like Earth. If it is too big, like Jupiter, it's too massive. The core of a Jupiter is very massive and it's holding this, gaseous envelope around it. So there are a lot of factors, for a planet to be habitable. So we still need to, look more into the atmosphere and sizes and distance of these planets from the sun. But the preliminary studies have shown that these two planets are closest to Earth. So you see the ESI index, 0.85, and there are these Arcos and other, potential habitable exoplanets. So based on all these statistics, right, we all can make a guess, right? Are we alone? Because this is also like century-old questions. I mean, even our forefathers, our ancestors, our grandfathers, great-grandfathers, they may not have been to colleges, they may not, have studied astrophysics, astronomy, but still they would look up and say, you know, are we the only creatures here on Earth? Are there any creatures up there in the sky, some other planets, some other galaxies? You know, like you see here, we have uh, you saw the candidates, the planetary candidates. There are billions of galaxies. Each galaxy has billions of the stars. Each stars are expected to have, some number of planets. So that gives us trillions of possible planets in our galaxy alone. So if one is in the habitable zone similar to Earth, there may be life. And plus, the other question is, what is life? How should we define life? Life like us, who need water, air to breathe, you know, or life, that do not need oxygen. There can be life forms in the micro scale, or even in the bigger sizes, and they may not need oxygen to survive, right? We usually see these crazy alien pictures, these from over. If you guys are a Star Wars fan, you might have seen these. This this is Luke in his planet, Tatooine planet. This planet goes around 2 stars, right? So far, we're used to with only one star system because it's our solar system. Our Earth goes around 1 star, but to let you know, more than 1/3 of all these stars in our Milky Way galaxy alone are in this binary star form. They are in pair. So if any planet around these stars, would look like this. In the evening, there would be 2 suns setting, and in the morning, there would be 2 suns rising. And maybe the creatures may not look like us. Maybe they are different. This is all speculation and guesses, and this is all science fiction now. But let me remind you, this picture here, this image here, this is taken from the Star Wars. And when Star Wars was made in '80s, nobody had confirmed, that there would be these 2 stars that would set and rise, in a binary star system. It was all theory. It was all, guess, probability. But in 2002, they found similar system. It was confirmed. The earlier I showed you, I talked about the Gamma Cephei. So Gamma Cephei is the first binary star system that was detected, that has 2 stars and one planet that would orbit the primary star. uh, I've done some extensive research on Gamma Cephei planet, its stability and habitability, and I did that work during my PhD career. I'm sure you can do a simple Google search and print that paper if you're interested. So let's get to these binary star systems. Right? So when I say the the stars, they can come in one star and number of planets around it, or they can be in the binary form, like these two you can see here. The two stars, they orbit each other around their very center, right? And there can be, and there are, the observationally verified systems that have three stars, the trinary star system. As many as quadruple star systems. So, four stars bound by their gravitational force, going around their common center of mass. Um, so there are, up to quadruple, maybe quintuple, but uh, and most of the detected systems are, either single star or the binary star systems. And even in uh, binary systems, as you see here, this a planet can be in S-type orbit, meaning a planet can go around only one of these stars, and both of the stars orbit their very center, or a planet can be uh, a P-type, meaning that planet can orbit both of these stars, like out here. So this top image here. And if it orbits the primary or secondary star, if the planet orbits one star, this is called S-type, or the satellite type. And if it orbits both of these stars, like this outer orbit here in the planet, it's called P-type. So the Gamma Cephei AB, the binary star system, the planet is in S-type orbit. It's going around the primary star, and these stars orbit this is their very center. And if planet orbits the primary star, it's called circumprimary. And if a planet orbits both of these stars, it's called circumbinary planets. You see, things get quite messy. When we go outside solar system, it's not, simple one star and 8 planets lined up. In almost coplanar cases, there are planets that have wild orientation with the stellar plane. The inclination vary a lot, the eccentricity varies a lot, and much more hostile. So again, my most of my research focus during my PhD career, and even today, I mostly work on these circumbinary planets and circumprimary planets. And I do a lot of stability analysis. We need to know that these planets, these stars, are in stable orbit for various reasons. To understand the physics of it, to understand the orbital mechanics, orbital dynamics. So if these two planes, so here the orbits of a planet and orbits of a star, and as you see, it's not that easy. These two orbital planes, when they intersect, there are like 6 orbital elements for each set, for planet, and if there's a binary set, that would be six orbital sets. So the stability analysis, helps us to understand each of these orbital parameters in detail, or what kind of role do these orbital parameters play in the stability of the system, the stability for long term, for million, billion, hundreds of billion years. Uh, if you don't know, much of these, they are. I mean, we all know the planet, the star planet system form an ellipse. So that means there are the orbital parameters come from the ellipse. For example, the eccentricity, what the shape of this orbit is given by the eccentricity. If it's a circular orbit, it is zero, but but in nature it's very hard to find circular orbits, so they are mostly eccentric. So that means they have eccentricity, and they have semi-major axis, meaning this tells us how far the planet is from the star, and the orientation of this ellipse, how it is oriented with the stellar plane, and as the planet go around this orbit, there are these three major angles that are changing: the omega, small omega, capital omega, or the true anomaly tells us, the position of the planet as it goes around the orbit. The other, aspect of doing stability analysis is the astrophysics. We want to know, the motion of n bodies under the gravitational influence, right? Um, Remember, our solar system, it is very quiet these days, or these years. It has attained a very stable uh, orbital motion. All of these planets. Before, few million year or a billion year after the formation, it was quite chaotic. Uh, we still, we still don't know exactly how the moon was formed, but we believe that there was not moon. Our Earth's natural satellite was not there. It came into existence when the other nearby planet, there was another planet called Theia, and when that planet collided with Earth, those two planets merged, and the remaining material was spit out in space, and that remainder of that material started to revolve around the Earth. Finally, all those materials coagulated, into one piece, and our moon was born. So to understand this astrophysical phenomenon, we do orbital stability. The other would be the astrobiology perspective. It takes not years, not 100 years. It takes millions. It takes billions of years for life to evolve. From this very hostile situation like these. Our Earth was, being bombarded by these asteroids every day, every hour. From those type of situations to get to a very stable orbit, where all those asteroids are gone, either they're collided with Earth have taken all those, fragments, the remaining parts of uh, the the solar system formation. You know, all those are gone, and it takes millions, billions years. Here is rough time. These are not exact time. There may be few change, of few change here, but roughly the formation of that happened about 4.54 gigayears, a billion years. So, about 5 billion years ago, Earth was formed, and first evidence of life, came after 3.5. So it took 1.5 billion years after the Earth was formed, and then, the first life were detected, and photosynthetic life form started like 2 billion years ago. And humans were less than 65 million years. Because they have 65 million years ago, there were dinosaurs, and the asteroid came in, and everything was gone, and that to restart again. And so it's like yesterday compared to, if you look at the whole formation period, humans came on Earth like yesterday. So for all these, we do these stability analysis. Um, let's. I want to talk so many things. I want to talk about my recent paper. This is GJ32 system. This is Glyceride 32 system. This system was originally discovered by Wittenmeyer and all 2012, 2014. This system has two planets, the inner planet. This is the inner planet. This is one star system. This is the only star system that I work, that is on one star. Most of my research is based on binary star. I'll come to my work in binary star in a moment. So this is single star. It has varies it, uh, the super Earth about 6 times the size of the Earth in a very close orbit. This is only 0.16 AU away. Compared to Earth, Earth is 1 AU away. That's how the distance is defined, 1 AU as Sun-Earth distance. So 0.16 AU is very close to a star compared. Our Mercury is more than 0.3 AU. And there is other system, GJ32b, that is about 3.56 AU away, and this is half the size of the Jupiter. Knowing these two, anyone can guess, can we, do some stability analysis or do some RV, radial velocity method, and generate a synthetic RV curve and, try and see if any other planet can lie in this region. Okay. And with that, we started all these. So this is the paper, and you can Google it if you want to read the whole scientific paper. I can. I don't think it's free. These publishers, they ask for money. This is published in Astrophysical Journal, but I can always send a PDF copy to Suresh, and Suresh can distribute you a PDF file, e-file. Nobody prints copies these days, anyways. I can give you a soft copy. These are all the orbital parameters of these systems. I'm not going into detail with these things. This is my undergraduate mentee. I help him do research. This is Mislek, G. Mislek. He was my PhD advisor. I still work with him as a colleague now. There are some of the numerical simulations, the calculation part, the simulation part you need to do. Anyone interested, or I don't know, if you ever go to college, you wanted to do astronomy, astrophysics research, especially planetary science, remember this name, Mercury package. Chambers, 1999, he wrote the package. It is free. You can download it anywhere in the world. You can download it in Nepal as well. And run it in your computer. It runs in laptop. It's just like, if you need to run for longer simulation time, millions, billions of years, and if you want to do, your initial conditions can be thousands. So in that case, you would need a much bigger desktop, much bigger computers with lots of processing power. But simple, orbital analysis, simple examples, like you can run a solar system. They have examples of solar system and see how the orbits look like, and you can do that in laptop. So simply download these. You can Google for Mercury orbital integration package, and then you can start your own research. And here are some other integration details that is not required here. So we did this. This was all this research. This part was calculated using the Mercury integrator, and what it shows here, this is 1 billion year simulation of that GJ32 system that we discussed. in that system, what we did, we injected like 15 Earth mass middle planet. So between those two known planets here, we injected like 15 Earth mass. That's the maximum size of the planet that it can be, in a stable orbit between these planets. When we found that size of 15 using the RV synthetic curve that I'll show you in a minute. Um, so looking at this image here, we could conclude uh, that these region here, about 1 AU, so this is distance versus inclination. We can just focus on the distance for now. So distance is, how far away it is from the star. So in this region, you can see uh, this greenish region here means a stable region. You can read the map, using this uh, color coding here. So maximum eccentricity. So eccentricity closer to 0 or 0.1, 0.2 means it's stable, the more circular orbit. As the eccentricity starts to increase bigger and bigger, it gets more unstable. The eccentricity starts to increase, 1, and maybe some of these are beyond 1, then these are hyperbolic orbits. Those are open orbits, they are unstable. So it shows, you know, all these other regions where the planet was injected, the eccentricity went, too high, up to 1 or more, and the planets were ejected from the system. They were not stable. If a planet cannot be stable, for a billion years or even less, some of these were ejected within 1,000 years, million years. So that means planet cannot be dynamically stable in these regions. However, in these regions, we found the eccentricity to be very, very low. And as a matter of fact, when I picked 3 regions here, these 3 regions denoted by asterisk here, and this is then I plotted a time series. It is a little different than this. This is a phase space map versus a time series, and I'm looking at the eccentricity versus time. And as you see, as time goes by, for 0 degree case, for this region here, this inclination means those two orbits, two planes of the stellar plane and the planet's orbital plane. The lesser that angle between those two planes, more stable it is. Higher up here, it's unstable. And for the lesser inclination case, IPL 0, all of these planets, the middle planet, the inner and the outer planet, seem to be in stable orbit for billion years. For higher, when we increase the orbital inclination 39, you see the eccentricity goes to up to 1, gets to 1, that means the system is unstable, and it also shows my internet connection is unstable. So, the other way to test is like, you put in these test particles. You can give some mass to these test particles or these massless test particles. So in this case, I put in 21,000 test particles and simulated for million. This one is done for 10 million years. As you see, these test particles survive here in these regions. This was the synthetic radial velocity curve that I defined earlier, the RV curve. So based on this integrated data, we generated these synthetic RV curves, and these curves showed that what's the possible maximum mass a planet can have. So in this case, we found about 15, the maximum mass of that middle planet, 15 Earth mass. And it can have 1 Earth mass. That was the maximum. So low it could go to 1 Earth mass. Even the Mercury-sized planets could be there. And one thing I'd like to point out is, you know, the RV curve, at that distance, this is the precision of the radial velocity, method, uh, mm, based on the, measurements that we have shown here. The RV for 1 Earth mass is like about 0.14 meters per second. That's a very small number. Right. Earlier, when I showed you the 51 pages B, the first RV curve, that was 50 meters per second compared to 0.14 meters per second. We don't have that sensitivity. Our telescope sensitivity is maybe 1 meters per second, or bigger than this. So you see, to get to 0.14 from 1 meters per second, there may still be a lot of work to do. So it's not that there are not any Earth-like planets out there. I believe that there are more Earth-like planets out there, but we are limited by our technology to actually go and test, see, look for all those planets. So if we want to measure, and this system is only 16 light years away, right? So if we want to measure, if we want to detect more Earth-like planets in this stellar neighborhood, we will need to increase the sensitivity of our telescopes. The concluding slide. So this is inner planet, that's outer planet. So this blue region is where the third possible planet can exist in a dynamically stable orbit around here. And the green zone is the habitable zone, meaning if there is a rocky planet or Earth-mass planet orbiting in this green zone, it can be potentially habitable. So this third planet, you see there's a small overlapping zone here. If, again, it's a big if, but if that's around these overlapping region, that planet can be habitable too. So this one I'm just doing the first. I told you what our exoplanets are and the big things, or the big picture of the exoplanet research. At the end of the day, you need to do some core research, and this example that I showed is part of my core research that I do. And of course, it's research. You get, when you get your research published, you get some award headlines. These are some of them that were published in various languages around the world. Some of them I don't even know what language they are. Seems like Chinese. The recent work was my recent work is on the stability of Kepler CVPs. So we look at all these circumbinary planets that are discovered by the Kepler Space Telescope. These are circumbinary planets, meaning these two stars, they are at the center and they go around each other. These are binary stars, right? So these stars orbit around each other, and there are planets around it. Some of these systems are Kepler 16, Kepler 34, Kepler 47, Kepler 38, and there are some more, right? And this work, this is my recent work. I'll again, this is published, and I can send you the PDF copies. Those of you who are interested, or Suresh can share with you all. The idea of this paper is to calculate this instability region. How far a planet can exist, or if you're looking in terms of star, looking from the side of a star, how close these planets can come in, right? So as these two stars go around each other like this, it has this unstable region around it, of course, due to due to gravity. They cannot get too close, and they will be pulled towards the star, or they can be ejected from the system. So there is this limit, the critical limit, the critical semi-major axis where a planet can exist nearest to this binary star system. That is the work, and we found some formulas, based on which you can. I shouldn't say we found formulas, but based on our numerical simulations, we set up this online repository where we put all the data, and anyone can get to those repository, download those data, and calculate the stability limit for their own system, for their own planet, based on whatever the masses of the stars or their eccentricity or their semi-major axis. If we look at the plot-wise, some of these data, you'll see in the paper, here the blue means the stable region, where planets can exist in the stable orbits, and the yellow ones are the unstable regions, and this distance is from the binary. So to the left, for example, and let's just Kepler 16. Kepler 16 is a binary star system. The masses or the mass ratio. What is the eccentricity of those? So based on the masses and eccentricity of these binary stars, these is the unstable region. So you see these lines here. They show the stable regions away from the star, and these are for different systems. What I'm saying is you can calculate your own critical semi-major axis, which tells the nearest stable zone. Okay, so yeah, that's and again, anyone interested or system error. Can you guys see this? I hope you can. So if you want to get these data that I just mentioned, you can always go to this website that I've shared the link with, and you can download this data. It also tells you, how to read the paper. It tells you how to download, where to download, and once you download, there are instructions on plotting the data. You can reproduce these images, these type of images here. You can calculate the critical semi-major axis, the stability, critical stable zone, between the stable region and the binary here. So I guess that's all that I have for today. If you have any questions, I can take them now. Thank you for listening.
Thank you very much, Dr. Satyal, for your wonderful presentation. We will proceed for the Q&A session now. If anyone has some questions, please come to this dais and please introduce yourself before asking your questions. Okay?
Namaste, sir. I'm Mustafa Siakati.
Hi.
My question is about space travel. In space, the biggest difficulty I see is the distance, space distance. Even Mars is 6 to 8 months far away from our current technology. Then how can we travel this very light year distances, 10 to 12 light year distances? Even TRAPPIST planetary system is around 39 light years distance. How can we travel that very big distance with our current technology so that we can be a multi-planetary species? Thank you.
So it was a bit like not off the track question, but he really wanted to know. I mean, how as you explained that there is a Earth 2.0, then how we plan to travel there? The human species will go there to make the universe multi-genesis species.
Yes, I mean, with current technology, like you said, you know, I mean, it's not impossible. It's just going to take years. I mean, even if we travel at the speed of light, to get to the nearest star system, it's gonna take more than 4 years or so. But the problem is, we don't have the technology to even get to have the speed of light. Um, for that, we need drastically new engineerings, new uh, new methods to travel. We cannot just burn oxygen, nitrogen, and travel. There has to be some other methods rediscovered, and that's why we need fresher, younger minds, to come and work in these fields. I mean, I am like you in this question. You asked me this question, and I asked that question to myself, and even I asked to some other astrophysicists. There is no, definite answer that I can give you. Okay, we need to do this. Honestly, I don't know exactly, what type of resources we would need.
Thank you for your answer. I guess the participant get the satisfying answer. So, is there any other queries from the audience? Uh, yeah, please. You can share your screen so we can have like two videos together. So if you close your screen sharing, then we will have this. Or else you want to show something to us?
Okay, that's fine.
It's still, the screen is still being shared. Yeah. Okay. We have another participant with his queries. Please introduce yourself first.
Namaskar, sir. My name is Jagannath Kodal. Sir, I have very few questions. First one is, you mentioned about ESI, that Earth Similarity Index, and in that index, the ranking of Earth was 1. Maybe there could be other planets that are more habitable than Earth, and Earth could be Earth may not be the ideal planet for life, and there could be like Earth index of Earth could be lower than 1, and there could be some planets that could be more habitable than Earth. And in Earth also there is oxygen, and but in early life, when there was life was evolving for the first time, the oxygen was poisonous to that life. There is evidence that oxygen is a poisonous gas for the early form of life in Earth. So we could be searching for other type of elements in other planets than oxygen. Oxygen could be the bad sign for life also. So what are your thoughts on this?
Yeah, I mean, that's a very good point. So there's a big debate. When we say habitable, that habitable means for like Earth-like habitable for human beings. Um, the point you said about oxygen, that's true. Initially there were some uh, these organisms, and that survived uh, on gases. There was other than oxygen. And when there was great oxidation and oxygen took over, then these organisms just faded away. So that means there can be, and there have been some organisms, some microorganisms found that have been surviving in the bottom of the Atlantic, where they have these volcanic eruptions with poisonous gas. So we have only one example of Earth, and we consider, okay, Earth is habitable, meaning it's habitable for the human beings. Um, there can be other planets, like I said earlier, and those planets, um, may or may not be in the habitable zone, and yet they can have their own form of life. Um, those life may or may not need oxygen. So there are many possibilities. And I'm glad you guys are thinking, beyond, what Earth, beyond what we see. But again, the goal for us right now, first of all, we want to find Earth 2.0, meaning, planet where human beings can survive, where there is oxygen and water. Uh, this is our current focus, but while looking for Earth 2.0 with oxygen and water, it is possible that we will, run into some other exoplanets with variety of life forms.
Yes, Utsav, we have the answer from our speaker today. We have we can take one more question today if you have any questions. Otherwise, we will wrap up because it's too late for Dr. Satyal back home. Thank you very much for staying with us and sharing your research. If you have questions, okay, please. We have last question, and then we will wrap up this session. Thank you.
Namaskar, sir.
Right.
So recently we have watched the Avatar movie, and there comes about the exomoons. So do you have technology to study about exomoons and like exoplanets? Can we study about its atmosphere and something to focus on life? Can we have we reached that technology, sir?
Yeah, that's another very good question. I'm always excited to hear these things. Guys, it's 12:30 a.m. midnight here in Texas, but I'm happy to be here up this late. Um, um, yes, exomoons is next, big um, research thing that's happening these days. After exoplanet, you know, I never mentioned about exomoon in my talk because we haven't found any exomoons yet, right? You can imagine in our solar system, Earth has one moon, one satellite. You go out, especially Jupiter and Saturn's, they have 60, 100 moons. I mean, depending on the size, you can have hundreds of moons. But there are so many satellites orbiting Jupiter and Saturn. And even Saturn's, and Jupiter's, some of these moons, you know, are, guessed to have underwater oceans. At least Europa, you might have heard, it has this icy surface around it. So that means with all these planets that we know outside our solar system, these exoplanets, at least 4,000 of them, uh, they may have the moon, the right size, and those moons can have life. That's very true. It's just the problem is, like you said, the technology. Do we have the right technology to detect those exomoons outside our solar system? No, we don't. It's very hard. The telescope we have, we do not have that sensitivity. I've worked on this project. We tried to detect these exoplanets. We developed a theory. There are two papers. again forward. I can give you the link to those papers. That paper, we set a technique, by measuring the radio waves generated by the exomoon exoplanet pair. We can, detect those radio waves here on Earth and confirm if uh, there is exomoon. So we also, requested some telescope time in this GMRT. It's in Pune, India, and we did some observation. We have the data, but unfortunately, we could not find any signal of the exomoon. So, it's uh, the the technology that we have is not sensitive, but I'm hopeful, in the near future, 1 or 2 years from now, we should be able to detect the exomoon as well. I can't hear you.
Thank you very much for your time today. Please put your mobile phone on silence. Okay, so thank you very much for your time, valuable time for us. I hope the participants had enjoyed today's session, and we look forward to their queries if they have, so that we can forward them to you, and you can answer on your time. So also we would like to thank the participants for joining us today, and we will put this video on YouTube and Facebook. So other participants and audience who our Facebook page audience who could not be here today will have an opportunity to watch this video and also put queries to you. So I hope, is that okay for you, Dr. Satyal?
Yeah, that's okay with me.
Yeah, thank you, thank you. Let's thank him for his wonderful presentation. So, do you have anything to say at last to the participants?
Thank you all for listening to me. Thank you all for being here. I hope you learned something. And always, think big, think outside the box if you are interested, and if you really want to work in astrophysics, astronomy, it's possible. You can do anything. Just you have to start and keep working on it. Finish your school, college, whichever level you're in. Go to university. Find a right way how to get to where you want to be. It's possible, and I'm always there. Suresh, NASO is always there to guide you in the right track, and we'll do our best to help you guys. Thank you.
Thank you once again. Thank you for joining.